So I have three stories that I want to talk about, but the first one, I'm going to do like a big kind of looping story about colliding galaxies first, and and just talk about why colliding galaxies are important and how they lead to the galaxies that we see today, including our own Milky Way. So here is a computer simulation that you can find on YouTube. And what it shows is the evolution of galaxies from the Big Bang forward. So even though the universe is expanding and and it's very uniform at first, slight anomalies or slightly denser areas will draw matter into them. And so even in an expanding universe, you actually expect portions of it to collapse. And the places where the collapse is occurring or where the matter is falling in or where galaxies are forming. So all the greenish stuff that you're seeing in the simulation is the gas. So this is gas that's out in between the galaxies, and they're clumping up because of gravity, and then they're also getting pulled in. And what you're seeing is the formation of a spiral galaxy there. And what is really interesting is that, well, many of you probably know that spiral galaxies, like our Milky Way, is very flat. Actually, here's another spiral galaxy, and the two are about to merge. And so the disk that makes up the spiral galaxy is actually made up of a lot of gas clumps. And then what you saw there was a merger of two spiral galaxies. And so there are a couple of different processes going on. One is there's gas that's fallen in, and that gas tends to clump up or to descend and build up the disk. And then every now and then you will actually have a merger between several large galaxies or a couple of large galaxies. And initially, during that merger, the disk will break up, but then the disk will build up again as more and more gas falls in. And of course, what is also happening is, and we don't really see this very well, at least in this particular simulation, is that stars are forming from the gas, and stars explode. They grow old. The most massive stars explode in supernova, and the massive stars tend to be very blue. And so, in another simulation later in the talk, we'll actually see bluish regions. And then, as the stars age, the younger massive stars have all died out, and what you have left tend to be redder and older stars. And so what we'll find is younger stars in regions and bluish stars in regions where star formation is still taking place. And then in places where there isn't much gas, you tend to find redder, older populations. All right, so that's sort of a generic spiral galaxy. There are other types of galaxies that have been found, and they, in addition to spirals and ellipticals, and it turns out that there's actually a really wide variety of really bizarre morphologies or shapes to galaxies. And so one of these is the so-called polar ring or the polar disk galaxy. And so what you see a ring of material that seems to be almost perpendicular to what looks like a regular spiral galaxy. So here's a spiral galaxy with spiral arms and a bulge in the center with older stars. And here you have a ring that's sort of perpendicular, and it's made up of these gas clouds, these dark dust lanes or dark clouds that are cold molecular clouds, and so they're dark enough and dense enough to obscure the starlight from behind. And these reddish regions are actually locations where stars are forming. And so there's so much star formation activity that the UV radiation from these stars are basically creating bubbles of hot gas, and they glow in the red of hydrogen light. So here are a couple other polar ring galaxies, and you can see just how bizarre looking they are. So again, you have what looks like a regular spiral galaxy, but then there's structures that are perpendicular to them. And so here's a formation scenario for polar ring or polar disk galaxies. And again, we're following this from the beginning, from the Big Bang. So the gas is expanding, but it's also collapsing inwards. And here you're building up the spiral galaxy with all this gas falling in and creating the disk. And here you can actually see slightly bluish tinge to the center, and that has to do with the stars. And then here we have another galaxy coming in, and because of the direction that it comes in relative to the two disks, and the angle of the relative angle of the two disks, you end up merging to form still a central spiral galaxy in the center, but you're going to have a collection of gas that makes up that equatorial ring. So now you can see that ring building up. So a lot of that got dispersed out during that violent collision, and but over time it recollects, and so now you have this sort of perpendicular structure around the spiral galaxy. And this is taking place over billions of years. So this is, if we look at something like this today, you just see a snapshot, and you don't see any of this happening, moving very fast. All right, here is a galaxy that's much closer to home, and it's actually real. This is the Andromeda Galaxy, the largest, the closest large galaxy to us. It's about the same size as our Milky Way, about 2.5 million light years away. So even though it's the closest, light still takes more than 2 million years to travel between this galaxy and us. And this is a very familiar view of the Andromeda Galaxy. And the Andromeda also has a number of satellite galaxies. This is M32, which is a satellite. And what I'm going to do now is look at the Andromeda in different wavelengths. So here it is in UV, in ultraviolet. And so the ultraviolet basically picks out those massive stars, those young star clusters. And so you can see bright splotches along the spiral arms where you would see the dust lanes. And so this shows you that star formation is taking place in those dusty molecular cloud regions. And then here is M32 again. And then I'm going to switch over to the far infrared, or the mid-infrared. And here, this is from the Spitzer Space Telescope, the spiral arms actually look almost ringish. And when this image came out, I mean, people were arguing and speculating about whether Andromeda actually had spiral arms like our own Milky Way, or whether the arms were ring-like. And so people have done a number of different computer simulations. This one is from this astronomer Dirix, and we're looking at the stars, and here we see M32, and what the simulation does is to insert in the small satellite galaxy, and they're able to basically generate structures by the passage of the small satellite galaxy that are very similar to the arms in the Andromeda Galaxy. And it turns out that in this simulation, the arms are spiral, but just because of the geometry that we're looking at, it's sort of tilted away from us. And so from the noisiness in the arms, they can look very ring-like. And there have been other simulations where the M32 is aimed directly at the center of Andromeda instead of off at the edge. And when it's aimed at the center, you can actually create very ring-like arms. But it's also, you have to be very lucky for this small galaxy to be aimed right at the center. It's more likely that it's going to be slightly off-center. And so this scenario is probably more likely compared to the total bullseye version. All right, here is a really spectacular galaxy that really is a ring, and there's no question about it. And not only is it a ring, but we're looking straight down the barrel of the ring. And this is something known as Hoag's object, named after the astronomer who first found it. And this image is taken by the Hubble Space Telescope much more recently. And what is really interesting is that you have what looks like the material that you'd find in spiral arms, and then you also have these bright regions where star formation is taking place. And so there are lots of bluish young stars that are being formed. And in the very middle of this galaxy is relatively old. And then there's this huge gap between the core and the ring. So there's a fall off in the number of stars. and there aren't many young stars here at all because it's yellowish orange, and so that tells you they're older stars. And what I wanted to talk about is actually this paper that just came out. It was published late last year, but there was press about it only this past month. And it's from a number of astronomers in Minnesota. And what they were looking at is this particular galaxy, PGC 1000714, and it looks like a face-on ring galaxy, like Hoag's object. But what they were able to do was to model the middle section and subtract it out. And when they did that, they found a second ring. So there's an outer ring and then an inner ring. And the outer ring turns out to be bluer, meaning it looks like there are, again, younger stars, more bluish stars, more star formation going on. And this inner ring is much, much fainter, and it appears not to have, it appears to be redder, meaning there's less star formation, less young stars. It's probably mostly old stars. And so the question now is, this is the first time we've ever discovered a double ring galaxy. And so how do these double ring galaxies actually form? And right now nobody knows because we only have one example of this. And so far this result is so new that the theoreticians, the people who run computer simulations, haven't really got a chance to take a crack at trying to simulate a double ring. But this is pretty exciting because this is the first example of a double ring. And ring galaxies are actually very, very rare. They make up about 0.1% of all galaxies ever observed. And these double ring galaxies, we'll see how rare they are, but they seem like they're probably even rarer. And then I'll close off on the story by showing one last simulation, and that has to do with this object, which was discovered in the constellation of Auriga, and hence it's called Auriga's wheel. And it's a ring galaxy, but instead of being face on, it's tilted almost 90 degrees. So you're seeing it almost edge on. And not only is there this, but there's also this weird looking blob that appears to be attached to it. And so there is a simulation that was done to try and show how this could have formed. And in this case, you have, again, a spiral galaxy, but now you have another galaxy come through, and it hits right in the bullseye. And when it does that, it caused this expanding wave of gas that, or of the gas clouds that expands outward. And so if you imagine Hoag's object, Hoag's object is basically this face on, where if this simulation is correct, this also, the central part, it consists of two galaxies that are in the process of merging, and in Hoag's object, that outer ring is basically that expanding ring of gas, sort of like a ripple expanding from a pond when you throw a rock into the water. And that gas is expanding, but it's also under high pressure, and so that pressure can help squeeze parts of the gas to start forming stars, and that's why you would have lots of young bright blue stars forming in the ring.